Hi friends, welcome to lecture 30. Till previous lecture, we discussed each concept uh, in depth with a beginner level. So this is lecture 13 of our ML beginners level series. And in this, we will discuss about training pipeline end to end from raw data to predictions and what are the all the steps it involves. So this is the bigger picture. So it starts with a collection of data from real world. For example, you may connect some data from sensors or you collect some data from user preferences. So you have some tabular data or maybe unstructured data like images and video. You organize that data in a proper format so that you can train some model. So that data which you have structured in a proper format. Now you split into train and test split. In the training data, you use this data to train the model and then you make the prediction. Out of this prediction, you use some cost functions to calculate the error. And then with gradient descent algorithm, you check for each parameter what kind of slope it is with respect to cost functions. And since we need to reduce the cost function value or the error, we update the parameter in the next iterations. In the updating the parameters, you train the model again. After updating the model parameters, you check again the predictions, then again you calculate the error, and this cycles repeats. Okay, and then in the end, when you are confident on training data, you say this is my general model and it is ready for the testing. And after testing, if you feel like good accuracy, then you can move forward. So step one is collection of data. So in the machine learning, data is acts as a fuel. Okay, the most important thing in the machine learning or AI is your quality data. So the quality data means how much coverage it has in the real world. For example, if you are trying to predict the image as a cat or dog, so how quality data you have? Quality data means in your image data set, how much coverage you have, like different scenarios, different scenes, different colors, different types of cat, so that it can predict in the unseen data, which can be anything. So more the coverage your data set has, better the model is, so that it can learn better. For example, house price predictions is one of the example in the regression model we have touched. So let's say you have area and you want to predict the price of the house. So you have input output mapping, and the better quality of data generalized leads the better model. Okay, better the quality data, you get a better model. Now quantity matters, but first the quality. Okay, step one is the collection of data. Second one is features and labels. Once you have data, you figure out that what is the output, what is your expecting output. Say in the house price prediction, it is a price, and it is labeled as y or output or label, we say. In the feature, what will be? It will be the X, which is the input, area, bedrooms, location, types of services available in that area, and these all the factors will affect the output. So all the factors which affect the output, which acts as an input, and which is also known as X, which is known as feature in the machine learning, and Y, which is known as label in machine learning, which is output, your the thing which you want to predict. So this is features and labels. Feature is X, which is input, and labels is Y, which is output. Okay. In step 3, you have that data. Let's say you have some 100 rows of data you have. So each row says one record or one entity, which has its own input, which has its output. So like this, you have 100 rows. Now you need to split it so that you can train on some data, and then you can check also whether your model is able to predict on unseen data, which is not seen before. So there you test the model and then say that, okay, my model is generalized enough to predict on unseen data. So train the model on training data, which is like most of the data you keep it as a training data, which is around 80% in standards and 20% in testing, which evaluates on unseen data. Okay. Now you build the model. Now you have data, training data you have separate, you have test data. So test data you keep it aside as of now. You have training data. Now you assume that what kind of model this data can fit into. So let's say you have a house price prediction. In that you have input as a area of a house and output as a price. Okay, so you have one input and one output. Now you assume that, okay, this data can fit into a linear relation. So you assume, you made these assumptions, okay, linear relation. So that you build the model on linear regression, since you know that this data may fit into a linear regression uh, as per your best knowledge. So you have two variables, one is m and one is b, intercept. So linear regression variable is equation is y equals to mx plus c. Why only one m and one c, which is a constant value or intercept? Because one input only there. If you have multiple inputs, let's say area, number of bedrooms is also there, then you might have 2m, m1x plus m2 x1 x2 plus c, because you have two variables, two input features. So you have two variables which needs to be adjusted during training. Okay, so you assume the model. So this is a step 4. In the step 5 you make the predictions. You have input, let's say 1500 square feet. You have model, linear model, which assumes some m value, some c value, let's say some random m values and c values, anything, it can be anything. Okay, then you make the predictions with given input 1500 square feet, with some as random values of m and c. You got that 60 lakh is the output price. But actually you know that for that training data, from training data you know that corresponding what is the y, you know that actually 75. The difference is the error. So you know that this is the error, you know, need to know. Now what else need to be done to improve our model? Calculate the cost. So calculating the cost, so for calculating the cost you need to figure out the cost function. So cost function, we have discussed one cost function in only very short. In intermediate series, we will discuss in depth. But as of now, you remember that in the regression, most common is, cost function is mean squared error, which average the squared error. So our error was in the previous slide 15 lakh. So 15 lakh, you square the error. Then you take the mean. Since it is a one output from one input, you take for 100, all 100 or 80 rows, whatever the data you have, you take all and then you square each error and then average it out, and you get one error. Okay, so that is a mean squared error. If cost is very high, if error is very high, cost is what? Error. Cost is high, error is high means poor model. If cost is low means better model. Okay, so here how you calculate the cost? You select the cost functions and then you calculate the cost value, and then on the basis of cost value you say that whether your model is good or bad. Now you have cost function and then cost function calculates the error. Now what you need to do, you need to update the parameters. Okay, update the parameters to reduce the cost function. For example, y equals to mx plus c, and then you predicted some output is 65 lakh, let's say. What was that? 60 lakh. Okay, sorry, it was 60 lakh and the original was 75 lakh. It means your parameter m or c needs to be adjusted and it's need to be higher. Okay, so how much adjustment is needed in the c, how much adjustment is needed in m, it is decided by gradient descent algorithm. Okay, to reach the minimum cost. Okay, so let's say this is y output or error or cost function, and this is x. The way the x varies, y varies, error varies. X means m or c. Okay, m and c, the way m and c varies, y varies. So you need to adjust m and c such that your goal reaches, the goal is minimum cost. Okay, error is minimum. Now you select the learning rate. So previously you selected M and C values, some random values. You calculated the error cost function. With gradient descent algorithm, you calculate the slope with respect to each variable also. Okay. So with respect to each variable, you calculated the slope. Now you need to adjust that, update the variable. For example, your M value previously it was 5. Your C value it was previously 2. Now you need to adjust it. How much you will need to add, at what factor? Let's say slope value came around 1.2 and here slope value came around 1.5. Now this slope value with respect to M for the cost function, how much you need to adjust it? Should you directly subtract 1.2 only slope value, but it might be very less? Should you multiply with some number, constant number, so that you adjust the value of 5 or M more, uh, more changes? Then it depends on the learning rate. Okay, so for example, the new weight, W or M new is equal to M old minus some learning rate into the slope. Okay, I'm not using any mathematical representation, but this is the simple equation during the updates of the weight. So you have learning rate, so you need to decide. If you take too large learning rate, then it may jump in between the minima. You may not reach to minimum value. If you take very small value, the new value update of M will be very slow and you will reach to minima at very long time, and it will lead your more computation of GPUs, right? So you need to define some good value or some value which can be fast enough and which can give you a stable learning. Okay. So training loop, this ML is a overall iterative process. Okay, you make predictions, you calculate the cost, you update the parameter, you repeat. Testing the model, you have a trained the model, you figure out the M and C values, good values. You feel that okay, on training data, error is reduced lot. Now you test the model on unseen data. If here also your accuracy is good on unseen data, let's say you have 20 examples which is not previously added into training data, and on this training testing data your accuracy is good enough, like let's say 95%, 90%, then okay, your model is performing well on unseen data, it is a good model. So overall this was the complete pipeline. Okay, this is the complete item. You have raw data, you decide features and labels X and Y, you split it into 80%, 20%, standard need not to be same. You decide the model, whether linear regression, some neural networks, deep learning, anything. Okay, we will discuss many models, decision trees, KNN, you might have heard. So this is all we will discuss, but in this step you decide the model, you make the prediction. You after making a prediction, you decide the cost functions. You decide what is the cost, or how cost needs to be calculated. Then you have gradient descent algorithm to update the weights, the way we need to update the weights. You decide the learning rate, at what factor you need to update the weights, update the parameter, a simple step of W, let's say W is the weight, so W new is equal to W old minus alpha into some slope. Okay, why we need to minus, why can't we add it plus? This we will understand in upcoming lectures about mathematics, when I will discuss mathematics about this. But as of now, you understand that this is the equation where we use for updating the parameters. Updating the parameters, again you make the predictions, calculate the cost, learning rate, which is same for in the one training loop, update the parameters, make the prediction. This loops continuously goes on till your error decreases. Okay, error is decreased. Now you have trained the model, you test the model, and then if your accuracy is good, you say that you comment that with these M and C values, or the assumptions of our linear regression model fits good enough on this problem statement of, let's say, house price prediction, where you have given area and you need to predict the price. So for this data, your linear regression or linear equation assumptions that this data is linearly connected assumption is correct. Why? Because on unseen data it is predicting well, so you can deploy in a production. So this was the summary of this lecture. So mainly we discussed about data, which is act as a fuel. The quality matters. Quality matters. Okay. Cost function measures the mistakes. Learning rate controls the updates. Okay. If you take big learning rate, it may be unstable training. If you take very small learning rate, then updates of parameter will be very slow and will be high computation cost. Okay. Model learns from data. It's all about learns from data, and in the data learning means what? You need to figure out the patterns or some structures, okay, or some relations. That's all. Okay, so that in the unseen data it can predict well. Gradient descents to reduce the cost. Okay, and then testing evaluates the performance on unseen data. So in this next lecture I will discuss about overfitting and underfitting. So as of now we have discussed overview. Okay, the different components in the machine learning end-to-end pipeline, end-to-end training pipeline. Okay, in the next few lectures I will go in depth in the very specific each concept. For example, in the features we will discuss about feature engineering basics. Okay, in the training test set, in the training data itself we have one train set, we have one validation set. Okay, during training also we have one data, we split the training data itself into two part. We will discuss that. In the model part we will discuss different types of models. In the cost function itself we will discuss different types of cost function and what type of model we use, which type of cost function. For example, in the category prediction we use different type of cost function, okay, and also why we use that. That way I will discuss. In intermediate series I will discuss about mathematics about that cost function. Okay, so this was all about this lecture. Thank you for listening. So like after this lecture, if you are able to just think that okay, this data and how training pipelines go from data to making the features, then split it, train test split, assume some model, make the prediction, calculate the cost. With gradient descent you updates the parameters, and then you train the model. Okay, so this iterative loops goes on until your accuracy decreases, accuracy sorry increases and your error decreases. Then you are confident enough that okay, this is model is good. Then you test on unseen data, and then if there also your accuracy is good, then you say that this is a generalized enough to fit into this kind of data. So thank you for listening. We'll meet in a next lecture with a very specific concept which is asked in many interviews. Okay, thanks.